Okay, good morning. We are going to continue talking about the area, you see, area under the curve, area of a given region. Remember, the other day we tried to, to introduce the new method in order to find the area under a curve. Okay, so just remind you what we did. So we try to finish it. That would end up with a new type of integrations. But you have to be patient to get through this one because we need the construction for future applications. So this is what we did the other day. You see the procedure was we want to find the area of a given region. So we just starting with the known area. If the region is going to be triangular, so it's easy because we know that the area of a triangle is going to be the product of its base and height divided by 2. Then if you know the area of a triangle, then you can find the area of a rectangle. Because if a rectangle is given to you, you can divide it in 2 parts, and each part is going to be a triangle. So we are going to find the area of each part and we add them together. But at the end of the day, there is a formula to take care of it. But we continue. If you have a kind of a polygon, if this is going to be the region that you want to find the area of this region, then we use the same procedure. So we're going to cover it with some triangles again. So we do have the area of a triangle. So we add them together and we get the result. Of course, again, there is a formula for it. But these areas, these regions are rectilinear, means the sides are just all straight lines. But there are going to be curvilinear area in everyday life. The best curvilinear area is a circle. So if you want to find the area of a circle, and we would like to use the same formula here. Since the side is a curve, so we cannot cover it exactly as we did it with the others. So what we're going to do, this is calculus. We are going to estimate it. So we estimate the area inside. We can estimate it by a polygon, if you like. And if you get a polygon, then you go back to this making triangles, then you'll be able to find the area. But of course, this area is not exact because these red parts are not covered. So what we would like to do, you have to get a so-called finer partitions. So you are going to increase the number of the partitions so that the leftover is going to be as small as possible. So you have to do it over and over and over to get the best estimate. So you may get, a sequence of numbers, and eventually, if you divide the circle into the infinitely many parts, then you'll be able to cover it. So that's a creation of the limits. That's the way the notion of the limits was introduced into calculus. So I talk about it that this method was used by Archimedes, and he just called it the method of exhaustion. It's very popular. He used this method to find the area of a circle, and also he used it to find the volume of some three-dimensional solids. But in calculus, this is not going to be our problem. In calculus, we are going to be interested in area under a curve, the graph of a function, okay? So that would be our concern for the rest of the course. This is the area that we are interested in. You see a function is given to you, it's nice and continuous. Your function must be positive because you're dealing with the area, which is a positive number. So what we would like to do is, we would like to find this region. We call it area under the curve. So how are we going to do it? We use the idea of the Archimedes. So we are going to partition it, you see. The way we partition it, we divide between A and the B into the 5 parts, 6 parts, 10 parts. And from each part, you get those vertical line. then you're going to get this set of rectangles. So if you find the area of a rectangle, add them together, that should give you the area under the curve. Again, the difficulty is as is with the circles, there are some leftovers. So what you have to do is you have to do your partitioning finer and finer and finer. And you have to pick many partition points to be able to do it. So the formula would be this one. We find the area of each these partial rectangles and we add them together. I use the sigma notation. Sigma means add. So this means I equal to the 1, we get the A1 plus I equal to 2, A2, A3 up to the AN. So this is going to be the formula for finding the area under the curve. But you have to give us instruction how we're going to find these partitions, the area of each partitions. Each partition would be a rectangle. And you know that the area of the rectangle is going to be the product of its dimension. This portion over here, it depends how many partition segments are going to have. So if it's going to be 0, this is 5. This distance is 5. So you may divide by 10, you may by 100, etc. So this is the one we refer to as a delta x. And in general, that delta x, okay, in general, delta x would be this one, because the full distance is between A and the B minus A divided by N. So this is the first thing that you have to find. So this is going to be one dimension of a rectangle. Now what's going to be the other dimension? This is going to be a y coordinate of a point. You see, y coordinate of the point. This one. You can pick this endpoint and find the y coordinate. You can pick this endpoint, find the y coordinate, or you can pick any points because all these vertical distances are the same. So basically, we know that this distance is going to be a value of a function at the point. So you can pick any point you like between, inside these rectangles and find the y values, which is f of ci. So this is going to be the area of one rectangle. So we put it into the sigma, take the limit and goes to infinity. Then you are going to find the area under the curve. So this ci is free. You can pick any number you like. But I fixed it the other day. The way I fix it, because we want everybody to use this one. But we arrive at the same number if you do using any other numbers. The way I fix it, I just pick the ci to be these points, the endpoints of those partitions. So this is A and the B. We talk about it. We divide it into different parts. So if you start from A moving to the right, so this point would be A plus 1 delta x. This point would be 1 plus 2 delta x. You see, x1, A plus 1 delta x. x2, A plus 2 delta x, etc. So if you want to find the xi in general, it's going to be A plus I delta x. So this is the one that I call it CI, because the CI is optional. I can pick any number I like. So eventually we fix the formula for the area under the curve. These are the area of each rectangles. You put them together and eventually you take the limits and you'll be able to do it. Before giving you examples where you do all these algebras, at the end, you arrive at the sum of the, a special sum of the numbers. You may have a sum of the, n integers, 1 plus 2, 1 plus 3 to the 4, 5, 6. You may have the square. There are some special one that we are going to use. There is only 2. So I'm going to give you those sum first, and then we give you an example. Okay, so these formulas are going to be used on the test. We give you this formula. You don't have to, you can bring it yourself. It's going to be part of the, on the test or any quiz on the final. We give you this one because we give you one problem from this partitioning one. There is a shortcut, but we would like to make sure you know it in case you want to take calculus 2 or calculus 3. Use this over there, okay? So you need the following formulas. If you are measuring computer science, you will see these formulas quite a lot in your fields, and they are going to prove it for you. But in this course, we are going to just list it. So when you do those problems, the first case that you may need is this one. You may have to find what is sigma of 1. You may have seen this probably in your pre-calculus class, but we remind you, sigma 1, I from 1 to n. What does it mean? This means sigma 1 is equal to, this means 1 plus 1 plus 1 plus 1, 1, 1, 1. How many times? N times. If this is 5, you add 5 ones. The result would be 5. If this is 10, you add 10 ones, would be 10. 100 hundreds. So in this case, you're adding n, okay, n ones. This is n times, n times 1 would be n. This is our first formula. Okay, so in short, it says sigma 1, I from 1 to n is equal to the. This is one of them that we may have to use. Okay, so we give you this formula. The second one is going to be, this is very popular for computer science. The second one is sigma I. Sigma I from 1 to n. Let's see, what does it mean? Sigma I means you replace I by 1, the result would be 1, plus, you replace I by 2, the result would be 2, plus, replace I by 3, that gives you 3. And you keep going. The last one is you replace the I by n, so that gives you n. They call it the sum of the n integers, n positive integers. And this is going to be equal to the n times n plus 1, n times n plus 1 divided by 2. Very popular formula. So in short, this is what you have to, you are going to use this one in all these examples. So this is the one that you can memorize it, but it's going to be given to you. This is going to be equal to the n times n plus 1 divided by 2. Very popular formula. As I talk about it, if you are going to be a computer science major, you're going to see this one in your course, discrete mathematics, and they prove it for you by using the so-called mathematical induction. But in this course, we are not going to prove it, but there is a piece of history that is not bad, you know, and you can prove it. This formula was proved by Gauss. You know, the Gauss is a great mathematician. Since his early days, he was very clever. So there is a saying that he just did this one when he was 7 years old. And this is the Gauss method, just for your fun. Okay, if you want to prove it using the Gauss method, this is the way he did it. He just lists the numbers. You see 1 plus 2 plus 3 up to the, okay, this is n minus 1 and n. Okay, this is exactly what you are looking for. Then what he did, he just write these numbers again, but in reverse order. So you start with the n, okay, n minus 1. You just continue to getting to the, okay, so getting to the, this is plus 2 and the plus 1. Okay, in reverse order, then he add them together. You see, if you add them together, this is going to be n plus 1, would be n plus 1. Plus, same thing here. You see, this is n minus 1 plus 2. Negative 1 plus 2 would be n plus 1. And he just repeated. You see, same thing here. That would be n plus 1, and that would be n plus 1. You see? So you're adding just n plus 1, n plus 1 is like adding the 1 over here. How many times are we going to do this one? It's n times. So n times n plus 1 would be n times n plus 1. as this is twice of the sum that you're going to be interested in. So your case is going to be, that's a twice, you just want one of them. So this means one of these, 1 plus 2 plus 3 up to the n would be whatever you have divided by 2. Just, this is piece of history, not bad to know it. But, if you are going to be taking courses, of the discrete mathematics, they don't accept this proof, of course. You have a mathematical induction, but it's not bad. Not bad to know the piece of history. Okay, any question? So that's a second one. The third one that we are going to use is, again, in computer science going to be used, if it's going to be I squared. And we need this one in one case in this course. So what's going to be sigma of, sigma of I squared, I from 1 to n. So sigma of I squared is 1 squared, 2 squared, 3 squared, up to the n squared. This is a very much more involved. There is no shortcut for this one. And it, again, is going to be proved by mathematical induction. It's going to be n times n plus 1. Okay, n times n plus 1 times 2n plus 1 divided by 6. It can be proved, in those courses. So a sigma of I squared, I from 1 to n, is going to be n times n plus 1 times 2n plus 1 divided by 6. We are going to use these three only. Of course, you can go on, find the I cube just for your information. We are not going to use it, but there are a couple of problems in your book that you may have to use this one. So for your information, but the one you see on the test, you are going to use this three part. But if you like, we can have other powers, sigma of I cubed, I from 1 to n. Okay, so this means the third power of those numbers. And this is going to be like the first one is the n times n plus 1 divided by 2 all squared. That's going to be the third one. The fourth, the fifth are more complicated to be able to do it. But again, when you take those courses, this is going to be part of your job to find them. Again, the way they are going to remember those big O notation that I talk about it, these collections are going to be used by, when you do some programming, and then you want to estimate, your time, estimate the money. So these are going to be the same as, remember big O that we talk about it, these leading term. You see the leading term over is going to be n cubed. So they say that this can be estimated by n cube. This is big O of the n cube. In computer science, they know what to do with the n cube, what's the operation involved. It's always the same. If you end up with the n, leading term would be n squared. If you end up with the n cubed, the leading term over there, your estimate would n to the 4. This is the way they like it now in those courses. But in calculus, I'm going to use it to give you an example for the area. Any question? So this creation of this area problem, we refer to it, Riemann, I talked about it the other day. But there is a piece of history, that the calculus is very important course. So different people talk about different origin of this type of problems. There is an Egyptian mathematician. His name in Arabic is Ibn Haytham or Haytham. And he was responsible really for this because he just created sigma IQ, and then the I to the 4 to the 5 to the 6 is followed. And he got this type of idea as well. But when you go piece of history, sometimes he was not appreciated. He has done something in physics, but in the part of calculus, he also was responsible for these type of formulas. You can check it on the internet. I've given a talk about it. Okay, so we are ready. I'm going to use that area problem for you so that you can see it, how are going to operate. Again, be patient. It is going to be a shortcut for all these, but if you want to continue getting more courses, these are going to be used as a special model in not only in mathematics, we're going to do in physics, whatever we did over here is the foundation of probability, okay, quite a lot. So that's why we are not going to ignore it. So let's give you one example. We give you one easy one on the test, but we give you one. Okay, so let's see what's going to be our example. We want to find the area of this. See, find the area of this region. Find the area of the region. Area of the region bounded by the graph. Okay, bounded by the graph of f of x equal to the 2x, okay, over this interval, over the interval, over the interval of what? 0 and 3. That's it. The one that we are going to be interested in is a little bit more, interested something like x squared rather than the 2x, but this is intentional. Okay, so there you are. Let's see what this type of area do you have over here, okay? Solution. Let's graph this, you need a graph, okay? So what is going to be the graph of, you are going to be interested in y equal to 2x, and you are interested in this interval only. So we are going to pick the x to be between, okay, between 0 and 3. That would be the job. So we need 2 points. You better use the 0 and 3 here. Okay, so this is it. X, y. If you put x equal to the 0 here, so y would be 0, 2 times 0. And if you put x equal to 3 here, so that gives you 2 times 3, which is equal to the 6. Okay, so let's get this area. This is it, this graph. So it's going to be the graph of the function. We have 0, 0. So this is going to be 0, 0. Okay, this 1 point, and then we have 3 and 6. 3 and 6. So suppose this is going to be 1, 2, 3. So that would be 3. Then I got the 6. So I pick 1, 2, 3, 4, 5, and 6. So this is going to be 2 points. And you know that this is a straight line. So you connect these points together. So that's a 6. Okay, so you connect them together. This is going to be the graph of the function. And you want it between 0 and 3 only. So this is 0, this is 3. So the area under the curve that we're going to be interested in is this one. Okay, so the area is a triangle. Okay, it's going to be triangle. So if you want to do it in geometry, you can do it. Okay, because it's a triangle. So if you want to stay with geometry, remember the area of a triangle. This is a right triangle, so this is going to be your height. Okay, and this is going to be your base. So what's going to be the area? So the area is going to be equal to the 1/2 of the base times the height. Okay, what's the base? Base is 3 units. So this is going to be equal to the 1/2 times 3 for the base, okay? And then for the height, this is going to be the height. And the height is, is 6 units over here. Okay, so that would be times it by 6. Okay, times by 6, 3 times 6 would be 18. The 18 divided by 2 would be 9. So that gives you 9. Okay, so A equal to the 9, whatever unit you have, is square. So that would be the area if you are in geometry. Okay, any question? But of course, what we would like to do Okay, so what we would like to do is going to be using calculus, of course, to get this one. Okay, so I just did this one and give you this example so that to give this number. Okay, so a is equal to the 9. So what we'd like to do, we'd like to do it with the with this partitioning one that we did have. Okay, so that's just for your reference. So what I'm going to do, I'm going to use your method of the calculus to do it. The method of calculus is that partitioning one. Okay, so this is going to be the case for the partitioning one. So what we are going to do is we start it over. So that was geometry. Okay, so I'm going to confirm it by using the method of calculus. The method of calculus is, of course, partitioning. So the area is going to be equal to, okay, the area is going to be equal to the limit of, okay, it's going to be the limit of the sigma, okay, limit of the sigma of f of ci, okay, times delta x, I from 1 to n, okay, n goes to infinity. This is going to be the case, okay. Now you have to form this one and just prove that this is going to be equal to the 9. Now, in order to do it, remember the format, this is going to be the case when, okay, this is going to be the case. Okay, this is going to be when delta x, remember, the delta x is equal to the b minus a over n. Okay, that's going to be your delta x, b minus a over n, and then we get the ci's, okay, and your ci's are going to be equal to the a plus delta x, okay, for I equal to the 1, 2, 3 up to the n. Okay, so this is going to be the formula that you have to use. The way we're going to use it, we start with the delta x first. Okay, so a and the b, a is the smaller number, b is the bigger one. A is equal to the 0. Okay, a is equal to the 0, and the b is equal to 3. Okay, then we go on find the delta x. So the delta x is going to be equal to the it's going to be 3 minus 0, okay, divided by n. So which is going to be simply 3 over n. Okay, so that would be the delta x. So we have the delta x. The delta x is equal to the 3 over n. Okay, so that would be the delta x. Then now you have the delta x, you start finding the CI. This is step 1. Step 1 delta x. This shows you how we're going to divide it. You see, it's going to be 0 to 3. How many? If you want to divide n parts, so each part must be 3 over n over here. Okay, so this is it. Now we're going to find the CI. So the CI, so that's step 1. Step 1 delta x. Step 2 CI. Okay, so the CI is going to be a plus delta x, a plus I times, sorry, there's I here. I delta x, I times delta x. If it's a C1, is 1 delta x. It's a C2, 2 delta x. C3, 3, okay? So that gives you CI plus, okay? So CI is a plus I delta x. Okay, I delta x. Now substitute, okay, to substitute over here, we have the, okay, we have the a is equal to the 0, so it's going to be 0, 0 plus I times delta x. So the delta x 3 over n, so it's going to be I times 3 over n. Okay, I times 3 over n, so this would be simply 3in. Okay, so this is the CI. So the CI is going to be 3I over n. Okay, and I is equal to the 1, 2, 3 up to the. Okay, so this is going to be the case that we're going to have. Okay, so this is going to be the CI. So we are here. Now we got the delta X, we got the CI. That's the second step. The third step is finding f of CI. You see, I'm going to find the area of one rectangle. Then when I find the area of one rectangle, I add them together, we get the area of the total one. Okay, so what we are going to do, we are going to continue getting what is f of CI. Now we start with the f of x. F of x is the function, is a 3x. Then you would like to find f of CI. F of CI. So you replace the x by CI, so that gives you 3CI. Okay, 3CI, but you do have the CI. So your CI is 3I over n. Okay, so f of CI is 3CI. So the 3CI would be 3 times 3I over n. So 3 times 3 would be 9. So that gives 9I over n. Okay, so this is going to be your f of CI. F of CI is equal to the 9I over n. Okay, so this is going to be the case that we are going to have. Any question?
Yes. Where did you get the 3 from? The f
Which
of x
one?
equals 3. I thought it was 2x.
Oh, is it 2? Okay, we change it to the 2. So thank you. That's a 2, 2, 2. So this would be what? Would be 6I, thanks. Okay, it's going to be 6I. Okay, so we have a 6I. I repeat it here, rewrite it. So f of CI is going to be 6I. Okay, it's going to be 6I over n. Okay, 6I over n, and I is equal to the 1, 2, up to the. Okay, so this is going to be the case. Any question? What's the next step? The next step is we'd like to find f of CI times it by delta x. Okay, so you can do all of them at the same time, but I prefer this one. So how about f of CI times delta f of CI? Okay, f of CI times delta x. Okay, f of CI times delta x is going to be what? So it's going to be 6I over n. Okay, 6I over n times delta x. What is the delta x? Delta x is 3 over n. So it's going to be times it by, times it by 3 over n. So this is going to be equal to the what? It's going to be equal to the 18I. Okay, 18I over n squared. Okay, 18I over n squared. And this is going to be the case. And now we are almost done with the preliminaries. So this is going to be 18I over n squared. Okay, again, you know that I is equal to the 1, 2, 3 up to there. So what you did so far, really, you find the area of one of those rectangles. Remember when you partition it into different parts, you say this is like this region, this is the region that you have. So what we are doing, we just divide them into equal parts, you see. This is what we're doing. So we find the area of each of these rectangles, you see. So we find the area of each rectangle over here, you see. And we add them together to get the total one. But of course, when we add them together, there are some left over here, you see, some left over. So that's why we replace and we do it over and over and over. When n goes to infinity, that gives us the result. Okay, so this is going to be the area of each rectangle. Now add them together to get the sigma. Okay, so the next step is going to be sigma. Any question? So And this is it. What is going to be the next step? The next step is going to be the sigma of, okay, the sigma of f of ci, f of ci delta x, okay, f of ci delta x I from 1 to n. Okay, so that gives us a sigma of 18i, okay, 18i over n squared and I from 1 to n. Okay, now this is where the algebra is coming. And the way we are going to do it, you see this sigma is on over I. Everything else would be considered to be constant. So you have to pull out everything else. When you pull it out, you are going to arrive at one of these cases that we introduced for you. You see, sigma on, sigma I, or sigma I squared. So in this case, you see, in this case, the number inside, you see, for this case, the coefficient inside, the extra one is 18 over n squared. So what we're going to do, this is going to be equal to, okay, it's going to be equal to the 18. Okay, it's going to be equal to the 18 over n squared. So the leftover would be sigma I. Sigma I from 1 to n. Any question? Always is possible. It's like the integration that we did before. Now you arrive at one of those formulas. You see, in this case, it's a sigma I. Then you have the formula. We already giving you the formula. Sigma I is n times n plus 1. You see, we give you this one on the test. You see, sigma I is n times n plus 1 over 2. So you have to substitute, simplify it. Okay, so this is going to be the case. So this is going to be equal to, okay, so this is going to be equal to, this is going to be equal to what? Equal to the 18 over n squared. Now sigma I. What is the sigma I? Sigma I is n times, okay, n times n plus 1 divided by 2. Any question? So you have to do everything at the end. You arrive at these three formulas that we talk about it. You get always a chance to simplify it. So simplify it first. Now we're going to simplify it. You see this 2 and the 18 would be simplified, would be 9. N and n squared would be n. Okay, so this is going to be equal to, what's going to be the leftover? The leftover on the top is going to be 9 times, okay, it's going to be 9 times n plus 1, okay, and divided by n. Okay, 9 times n plus 1 divided by n. Now, this is what? This is now the sum of these partitions that you find. But as you know, there are a leftover here. In order to take care of this leftover, we are going to increase the number of the partition. You see, if you increase the number of the partitions, you are going to have more, you see, more triangle. So in that case, these leftovers would disappear. So how are you going to do it? By taking the limits, okay? You take the limit of whatever you got over here. You see the limits. You take the limits and goes to infinity. And we already talked about limit at infinity, remember? For the limit at infinity, we use those partitioning one. So what I'm going to do, I'd like to do it here so that you can have it here. Okay, so I do it this green part of it here. Okay, so going up there, and now we say, oh, we know that the area is going to be equal to, okay, the area is going to be equal to the limit. Okay, it's going to be equal to the limit of what? Limit of n 9 times n plus 1 divided by n. Okay, when n goes to infinity. Okay, limit of 9 times n plus 1 over n when n goes to infinity. Now you know that for this limit, we just shrink it. So this is going to be equal to the limit of the leading term on the top. You see, if you multiply the 9 inside, if you like, it's going to be n goes to infinity. So inside we get the 9n plus 9. Okay, 9n plus n, 9 over n. 9n plus 9 over n, and goes to infinity. When it goes to infinity, this part would be, you see, you get the leading term. So it's going to be limit of Leading term on the top is 9n, on the bottom is n goes to infinity. So that gives you 9. So A equal to the 9 is going to be the area, of course. Okay, the area and then the care. Of course, this is a very easy example. If you make it a little bit more complicated, sometimes would be almost impossible to find. But it can be done. And this is mathematics. You suffer first, okay, then say, oh, let's go and find a machine for it. So that machine would be our new notion of integration that I'm going to introduce it right now for you. But that gives you an idea of how this happened, okay, how these great theorems, if you like, would come true, if you like, and to be done. Any question on this one? So that's the fact that you have to know. You have to do it once for us. Let me give you more example in a minute. But what we can do is, this is, you see that the idea of the area is just an excuse. We talk about the area. If you want to stay with the area, it's kind of classic. It would be a classic problem. Classic, is like literature, classic literature, music. So there would be a boundary restriction. The restriction over here is just, you have to do it, you can do it only for the area. But what we are going to do is we are going to start it over. We create a new machine. Exactly that machine would be very similar to the one that we did. But at the end of the day, our machine would be connected to the notion of integral. And then we'll be able to do all these in a short form. Okay, so I'm going to introduce that type of integral that will result on this. And then we come back and we do this problem in 2 seconds. Okay, any question? So you have to get to use this, because these are the type of arguments it's used for many other part of science, if you like. Okay, in physics, probability, I'm going to introduce that integral, then I come back and explain it to you. So what I'm going to do, I'm going to use the same procedure, but I'm not going to call it integral. I'm not going to call it the area. Okay, this is a notion. So that was all, it started with the idea of the arguments. But it was the Riemann, okay, great German mathematician who just created this idea. Why we just going through all these details? Let's do it in the short form. If you want to do it in the short form, you have to introduce a new machine. What is that machine? That machine is called definite integral. Remember, we already talked about indefinite. Indefinite integral is a function, is the notion of antiderivative. But this one over here is different, but they are going to be connected to each other. So what is going to be definite? Definite integrals. It would be connected to the area problem in a minute. Definite integral, and of course, we honor the Riemann. The Riemann, if you are a math major, you are going to refer to this one by this name, Riemann integral. Great mathematician, you can search on internet and read about his life story. It's quite interesting. Now, what's going to be Riemann integrals? You see, I'm going to use the same procedure that I did for the area, but I create this notion. So let's see what we did with the area. You see, we start with the function and we assume it must be continuous, must be non-positive. No, just start with any function you like. Okay, so this is it. Suppose a function. And don't worry about some expression that you may be unhappy about it, but it's mathematics. You are going to build something big. Okay, suppose a function f is defined. Okay, suppose a function f is defined on the closed interval. On the closed interval. Defined on the closed interval is going to be a comma b. okay, such that is going to be such that for any partition. Remember the way I partition A and the B, that interval is the same thing. Suppose the function f is defined on closed interval A and B such that for any partition, the point of the partition as we did it before are going to be x0, x1, x2, up to the xn, any partition of the closed interval of A and B. Okay, when those partition points is, the first one is A, next one is x1, x2, okay, x3, etc. Up to the last one is xn equal to the B. So this simply means this is, you see, this is going to be your A, and this is going to be your B. You divide it into different terms. I divide into equal part, it doesn't matter, but the equal is easier. So this is, if you divide it into equal part or otherwise, doesn't matter. But eventually we are going to be interested at the theorem, you see, that's it. So as you can see, this part, this is going to be x0, and this is going to be x1, x2, x3, you call the last one xn. It's like the one that we did for the partitioning those triangles. Okay, so if you have a 0 and 6, so the length is 6, you divide by 100 parts, 10 parts, etc. So it's going to be called any partitions. So we have a function. This function is nicely defined on a closed interval. So what we do is we are going to pick any partition you like. I like my partition to have 100 points, 100 parts. You may like your partition to be 50. Somebody else may be 20. It doesn't matter. For any partitions. Now this is going to be a partition. Now I'm going to pick those CIs. Okay, any partition x0. Okay, of this interval. Okay, and any choice of those CIs, and any. Okay, any choice, selection, choice of CI. Okay, CI between xi minus 1 and xi for I equal to the 1, 2, 3 up to the end. Okay, so this means what I did. This means I've already got that. You see, I've already got that. I've already got that A and the B. Okay, and these are the points that you did have, partition points. X1, X2, X3, okay, X4. You continue to the, continue to the XN. So what I'm going to do, as we did it for the other one, I'll go to the first partition. Okay, I pick 1C. I call this one C1. I'll go to the next one. I pick another number. I call it C2. I'll go to the next one. I take the C3. Then I continue. Okay, I continue somewhere over here. I pick the CN. Okay, so as we did it before, but it's not area problem. We just do it as we go on. So we get any partition we like. We go inside the partition, and from inside each of these sub intervals, if you like, you pick one of these CI. So you're going to have what? So you're going to have a C1, C through, okay, C4 up to the CN. Okay. And then what I'm going to do is, again, as we did it for the other one, I got the CI, then I drop it into the function that gave me f of C1. I drop this one into the function that gave me f of C2, and then I continue. That give me f of Cn. So for any partition, any CI that you pick, then what I'm going to do, I'm going to form that limit. Remember, if you do all these, then the limit that you call it the area, but we are not going to call it the area in this case. Okay, the limit, this is the limit of sigma of f of ci delta x, okay, I from 1 to n, I from 1 to n, and n goes to, okay, n goes to infinity. Okay, then the limit of f of ci delta x, I from 1 to n goes to infinity. This limit exists. Okay. So if you do any partition you like, you say you pick one partition, 100 parts, you pick the CI, you find this limit is happen to be 5. But if I do, I'm somebody else, okay, if I divide this one into the 60 parts, I pick my CI, add them together, bring these limits, and I arrive at the same number. Somebody else, some numbers, same numbers. So for any partition between A and B, any CI, if you find this limit and this limit happen to be the same all the time, if this is going to be the case, then we say, oh, this function is integrable. Then, okay, then f is said to be, okay, is said to be integrable. Okay, is said to be integrable. Okay, it's going to be integrable, or if you want to honor the Riemann, or Riemann integrable. Okay, Riemann. Just the name, integrable. Integrable on the closed interval of A, comma B. Okay, it is a little bit different from ordinary limit, because ordinary limit, you just find this limit, like the area problem. But this problem will tell you that, you have this limit would be unchanged for any choice, whatever you want to do, whatever CI you want to take. But at the end of the day, this limit would be always the same. You may get different numbers, but when you may get the different expressions, but when you take the limits, okay, that limit would end up with the same number. Okay, then f is said to be integrable, or Riemann integrable on this interval. Okay, if this is going to be the case, then the number that you got from here, we have a special notation for it. So in this case, if the answer is positive, in this case, okay, in this case, the definite integral, okay, so that's going to be Riemann integrable. Now in this case, the expression, the definite integral, okay, the definite integral, or a Riemann integral, or a Riemann integral, okay, the definite integral, or the Riemann integral. That number that you got from here, we call it the definite integral. Okay, are you done? To go to the next page. So in that case, the definite integral, or the Riemann integral of the function, okay, of the function, okay, of the function f on this interval on AB is going to be denoted by, look at the notation, it's the same integral as you did before, but it's going to be integral from A to B, f of x, d of x. So if you see these numbers over here, your integral is definite integral. The result is a number. If you don't see the A and the B here, your integral is indefinite, antiderivative. that we did it before. The result is a function. Okay, so the difference, make sure you know it. So in this case, it's going to be denoted by integral from a to b f of x dx, and of course is defined by that formula, and is defined. Okay, it's going to be defined by. Okay, it's going to be defined by. This is it. Integral from a to b f of x dx. Okay, a to b f of x dx is going to be equal to the limit, okay, of the sigma of f of ci delta x I from 1 to n, and n goes to infinity. You see the one that you call it the area under the curve? Now we are going to call it something else. We call it just a number. Of course, if you see, of course, quickly, if your function is continuous, in particular, if f is going to be continuous, if f is continuous, and of course positive, and non-negative, and non-negative on the closed interval of a and b, then of course this is just the area problem. Then the area under the curve, a equal to integral from a to b f of x dx, okay, is simply is the area. Is going to be the area, okay, is the area of the region, area of the region, under the curve, under the curve, okay, and the curve y equal to the f of x from x equal to the a to x equal to the b. You see, nicely we introduce a new mathematical machine, if you like. That machine is going to be definite integral. You see, you are not going to now bothering with the area all the time. We focus on this machine. And if you can find a formula for this machine, then the area problem can be done quickly. So we have two types of integral. This integral is definite. Okay, the result is a number. The other one is antiderivative, which is a function. So the question is going to be, is there any relationship between these two? Yes. There is a nice relationship that we're going to discover, and everything would come together. But we have to give you a couple of examples first to see how we're going to handle this one for us. Because this is going to be the machine that we use in future for all application in science. They are all definite integral. Most of them are definite integral. The foundation of the probability is this one. Okay, so what we are going to do, I'm going to give a break now. Take your break, we come back. We take one example, one more, because we give you one of this, like this, not the area. So we give you one example to see how we handle it, like the one that we did, but it's a little bit more involved. Then we find the connection between this integral and the previous one. And at the end of the day, everything would be nice. There's not going to be any new formulas, okay? So it's a 9:04, okay? So can have 10, 12 minutes. We come back and we continue with this notion. Okay, that will take us to the end of this chapter, in a matter of today and tomorrow, of course. Take a break and we come back. See you then. Okay, we are going to continue. So, so this is going to definition that we have. So I'm going to give one example first, okay, to see how we're going to operate. This is the procedure is like the what we did for the area and the curve, okay, but that gives us more freedom. Okay, then we come back and we simplify it and give you easier method to find it. Okay, so this is how we're going to see it on the test. We give you one on this test and one on the final. So it's going to be the example. I was just remind the APC remind me that for the final exam, so they offer only 2 hours exam, okay, because the exam time for from the college by the college is 2 hours. So if you want to arrange your appointment or make an appointment, keep in mind it's going to be two hours, not 2.5, because the official one of the college is 2 hours. And we give you 12 questions. So there are going to be 13 questions. You can answer 12. Okay, just remind. It's going to be mostly the questions going to be mostly from test 3 and quiz 4. Okay, then we remind you that. So let's check the example. This is the way we're going to do it. We're going to say use definition. Remember, some of you miss this one for the differentiation. When I say use definition, you just use formula. Yes, there are going to be formula for this one too, but you're going to use definition only. You see, we give you one, we would like you to use definition for. Use the definition. No formula. Okay, use definition of the definite integral. That partitioning one. Definite integral. Definite integral. To show, to show that integral of 0 to 3, see that's a definite integral, now you know it. X squared dx is equal to the 9. We want to use that partitioning formula that we talk about it and prove that this integral is equal to the 9. Okay, are you ready? Definition means this. Solution. Get the definition, you see, 0 to 3, just that the area definition. X squared dx is equal to limit. Whose partition? Limit of the sigma of f of ci delta x I from 1 to n goes to infinity. You see, this is it. And remind you, where or when delta x is equal to the b minus a over n, okay, n, and ci is equal to the a plus I delta x, okay, for I equal to the 1, 2, 3 up to the end. That's your formula. Of course, this CI is optional. You can pick any CI you like, but this is the easiest one, okay? And would like everybody to use this one. So just like the area problem, step by step, form this one. Remember the way we do it? Step 1, delta x. So what is A? A is the smaller number. B is the bigger number. Find delta x. Delta x is equal to b minus a, 3 minus 0. 3 minus 0 divided by n. So that gives it 3 over n. That's your delta x, step 1. Any question? Step 2, ci. What's a ci? Ci is a plus I delta x. What is a? A is 0 plus I times delta x. What is delta x? Delta x is 3 over n. So the result would be 3i over n. This is Ci. Question? Next, f of Ci. What is f of x? F of x is the function, x squared. Replace the x by Ci. F of Ci is Ci squared. But what is the Ci? Ci is 3i over n. 3i over n all squared. Squared, you square the top, you get the 9i squared. Square the bottom, we get n squared. That is f of Ci. Question? Next, f of Ci delta x. Multiply them together, f of Ci delta x. F of Ci times delta x equal to f of Ci is 9i squared, okay, over n squared. F of Ci times it by delta x. Delta x is 3 over n. Times it by 3 over n. Simplify is equal to, you cannot simplify and multiply 3 times 9, 27. I squared divided by n cubed. N cubed. That is f of Ci delta x. Question? Next. You see, we did everything inside. Sigma. Add them together. Sigma of f of Ci delta x I from 1 to n is equal to sigma of this one. 27 I squared divided by n cubed. I from 1 to n. Now we have to evaluate this one. Remember, everything other than the I are going to be considered to be constant. You have to pull them out. Extra one, 27 on the top, n cubed on the bottom. So this is going to be equal to 27 n cubed. The leftover sigma I squared. I from 1 to n. Okay, so pull out everything else other than the I. Any question? Now this formula would be given to you. Remember, it's the one you see on the test, or you bring it. Let me give you this. Sigma I squared. N times n plus 1 times 2n plus 1 over 6. So you substitute to simplify it. So you continue is equal to the 27 n cubed times it by n times n plus 1 times 2n plus 1 divided by what? Divided by 6. Simplify it. How are we going to simplify? You see 1n would disappear. That gives you n squared. 6 and 27 by 3, 2 by 3, 9. Leftover on the top is equal to the 9 times n plus 1 times 2n plus 1 divided by 2n squared. You see, this is how you simplify it. Any question? Last step is take the limit. Okay, you take the limit of this last one. So the limit of 9 times n plus 1 times 2n plus 1 divided by 2n squared. N goes to infinity. You see, now you have to use that leading term idea to take the limits. The leading term on the top is a product of this. You see 2n, 1n, and the 9. So it's equal to the limit of leading term on the top 9 times n times 2n, 18n squared. Leading term down the bottom, 2n squared. Because when we take the n limit at infinity, remember, limit at infinity, we just focusing on the leading term of the polynomial. So n squared and n squared would cancel out. N goes to infinity. So 18 over 2 would be equal to the 9. That's it. We did it. Integral from 0 to 3, x squared dx is equal to the 9. And then we're done. You see, it's a very nice, nice application, really, that you will see it. But of course, it takes time, and this is an easy example. If the example is getting complicated, we won't be able to do it. Okay, but the thing is that we have two different types of integral. This is a number. The previous one was a function. So the question is going to be, is there any relationship between these two? Yes. That relationship is going to be called fundamental theorem of calculus. And what is that relationship? You see, not for this one. If it's going to be the test, you are not going to use this method. You see, the theorem will tell you that if you want to find this integral, it's 0 to 3 x cubed dx is equal to simply, you integrate it first. You see, integral of x cubed, antiderivative is x to the 4th over 4. I'm sorry, that's x squared. It's going to be x to the 3rd over 3. Remember, previously we had the constant c. Now we are going to evaluate this one from 0 to 3. So the top, you replace x by 3, that gives you 3, okay, cube over 3 minus 0 over 3. 3 cube would be 27. 27 over 3, and that would be 0. 27 over 3 would be 9. The same answer. But of course, I didn't use the definition, you see. Would like you to do one of them using the definition on the test for us. But of course, in general, we are going to connect them together and using that theorem. I'm going to give you the theorem. We call it fundamental theorem of calculus or of integral. Any question? So this is a very nice method. We are going to use this one to, okay, to prove theorems, to design some mathematical modeling. So that's why you have to know it. But practically, if you want to do the problems, of course, this method is not going to be easy to handle. That's why we connect them together and you have this famous theorem, okay? In your book, I think it's in 4.4, the fundamental of calculus, because everything else is the one that we talk about it. So just double check it. And that would take, make things so easy for us. Yes, the one that I did so far was 4.3. So this is 4.4, and that would be make things so easy for us. Okay, so what is fundamental? Fundamental theorem of calculus, we call it. Some people, they say integral, but it's calculus. Great, great results. So what is this result? It was proved, in the history of calculus, the people, they were doing integrals separately. Some people, they're focusing on antiderivative. Some people on the definite integral. So the question was, can you connect them together? The answer is yes. It was done early days, even by Newton or Leibniz. But later on, it was introduced by Cauchy, Agustin Cauchy, and that's a theorem. Two types of integral, we connect them together. Remember, the first one is this one, antiderivative. So suppose after this theorem, things getting so easy for you. Suppose f is a continuous function. Is a continuous function on the closed interval of a comma b with an antiderivative and antiderivative f such that, okay, such that, there you go. This definition of antiderivative, f prime of x is what? Is equal to the f of x for all x in this interval. Remember, this is the first one that you are familiar with, antiderivative. Now, next one, we say, oh, if this is going to be the case, then the function is integrable. F is integrable. Integrable means we can do partitioning one to find the integral. Integrable on a comma p. So this means integral from a to b f of x dx exists, and the definite integral a to b f of x dx. If you want to find it, you just simply find the antiderivative. Remember, the antiderivative is just f of x. We have the formula, we can do it. Find it, don't add the constant c, evaluate it from x equal to the a to b. Okay, this is it. We say from a to b, which is the same as f of b minus f of a. That's it. That gives you so, make it so easy for you. Or if you like, integral from a to b f of x dx, Riemann integral, is simply antiderivative at b minus the antiderivative at a. It's a great theorem. We call it fundamental theorem of calculus. Any question? You see any field of mathematics that you study, they would have a great theorem that they call it fundamental theorem. For example, if you do arithmetic, if you work with the numbers, fundamental theorem of arithmetic is prime factorization. We'll tell you that any number is a prime or is a product of primes. You see 6 is 2 times 3. 2 and 3 are primes. 7 is a prime number. So that's a fundamental of the arithmetic. So if you don't have that formula, that theorem, you can't do anything in arithmetic. You have one in algebra. What is fundamental theorem of algebra? What do you do in algebra? Whatever you do in algebra, at the end of the day, you solve equations. So fundamental of the theorem of algebra will tell you that every equation would have n solutions. If you have quadratic equation, you get always 2 solutions. If you have a cubic equation, you get 3 solutions. Of course, some solutions are going to be complex numbers. In the case of calculus, this is the fundamental of calculus. Okay, so it's just simple. Now, we don't usually prove it, but it's not difficult to prove this one. If you want to prove it, I talked about it before for you that every important proof in mathematics must go through the mean value theorem. I just give you a short proof just for a record, you keep it, we are not going to ask you to prove, but so that you will see why I was focusing on the mean value theorem. See, I just connect these two together for you. So this is just for information, not bad. It's a great theorem, piece of history, and the proof that I give you is not in your book. So it's a very short proof and a nice one. If you're going to be a math major, these type of techniques are going to be used. Okay, so what I'm going to do, I'm going to prove it for you. So what I should prove? I should prove that this is it. I should prove that, note that. What is this integral? You see, remember, if f is going to be integrable, integral from a to b, f of x dx. Remember, it's going to be the sigma of limit of the sigma of f of ci. Remember, times delta x, I from 1 to n goes to infinity. That is the definition of a Riemann integral. Okay, and you know that when Ci is any number, okay, between any number in this interval, in the interval of xi minus 1, comma xi, for I equal to the 1, 2, 3, up to the n. That's a formula for the definite integral. But what I'm going to do, I'm going to bring the mean value theorem. Remember this function f, c, you say that f is differentiable. Okay, is differentiable on the interval of xi minus 1 and xy. And so the mean value theorem, remember the MVT, can be applied. Remember, can be applied. So what is that? Remember, f of b minus f of a is going to be f of xi minus f of xi minus 1 is equal to the f prime of a kind of ci times xi minus 1, sorry, xi minus xi minus 1. That's the mean value theorem. Remember, f of b minus f of a equal to the f prime of c times b minus a. But see, this f prime is antiderivative, is equal to the f of x. So we say that, oh, but f prime of ci is simply f of ci. And this is just a delta x. Delta x is equal to xi minus xi minus 1. If you put them together, so this is what you have. F of xi minus f of xi minus 1 is equal to the f of ci times delta x. You see, I connect them together here. This is a proof that was done by Cauchy. Take the sigma of both that side, and you get what you want to prove. Take the sigma of f of xi minus f of xi minus 1 equal to the sigma of f of ci delta x I from 1 to n. Okay. This is the one that I want. I want to simplify this part. Okay, I equal to the 1 to n. Let me simplify it for you. Again, we are not going to ask you to prove it, but it's nice to know. So I'm going to open up this one and show that this is f of b minus f of a. You see, if I take the limit of both sides, this would be integral, and this would be f of b minus f of a. So let me show you that this is f of b minus f of a, and then you're done. If you open up this sigma, you see, note that it's a great techniques. So if you open up this, you see you have f of xi minus f of xi minus 1. I from 1 to n. Substitute. You see, if you put I equal to 1, so that you f of x1 minus f of x0. That's the first one, plus if you put I equal to 2, so that gives you f of x2 minus f of x1. If you put I equal to 3, that gives you f of x3 minus f of x2. Then you can continue. The last part, if you put I equal to the n, that give f of xn minus f of xn minus 1. Look at these, you see f of x1 and x1 would cancel out. F of x2 and x2 would cancel out. F of x3 and x3 would cancel out. Everything would cancel out. Except, you see, all these would be canceling out, except these two numbers over here. We call it, in calculus, we call this one a telescoping sum. This means it's like looking through the telescope. If you look through the telescope, the first thing that you see and the last thing, if you like, the telescope will bring it forward for you, up in front so that you can see it together. So this result would be equal to, this is f of xn, and this is f of x0. Xn is the last part of your partition. So this is f of b, and this is f of a. Nice, you see? So I proved that f of b minus f of a is equal to the sigma of f of ci times delta x, I from 1 to n. Take the limit, and then you have it. This is a constant, you don't need any limit. So the limit of the sigma of f of ci delta x, I from 1 to n and goes to infinity, is simply f of b minus f of a. So this is simply integral from a to b, f of x dx, and this is f of b minus f of a. If you like proof, this is a piece of history that I just write down for you. But of course, we are not going to ask you to prove it. I show you how we use mean value theorem. I told you it's a secret in mathematics, that if you want to do something great, then you have to go through this mean value theorem. Okay, so getting back to what we are going to do is, this is it. This is the plan. We give you this, and we ask you to find it. So what you do, you forget about A and the B. An antiderivative, the formula that we did have before. You find the capital F here. Then you evaluate it from these two numbers, and then you're done. Okay, you get something like 4 problems related to this formula, and we are almost done with this chapter. Okay, so I'm going to give you those examples one by one. Okay, so that was a proof, just for your information. Make sure you understand the statement of the theorem. This is the statement of the theorem. If you want to find the integral from a to b f of x dx, this is the definite integral. Means forget about a and the b. Find antiderivative. But when you find the antiderivative, it's a function. Evaluate it. At b, then a, subtract. Okay, so you don't need this partitioning one to be able to do it, and we can do it. That's why we give you the formulas first. Okay, so let's get an example to get to know it. Don't be afraid of that formula anymore. That's it, your job. Evaluate each integral. Evaluate each integral. We did all the hard part of this chapter. There are a couple of definitions only. This is, of course, a definite integral. You see, this is it. Integral from -1 to 2, 4x cubed minus 2x plus 2 dx. That's it. When you see these numbers, it's a definite integral. So you have to use this theorem that we talk about it. First thing to do, forget about the numbers. Find the integral. You know that if there is any radical, you rewrite it. Any fraction, you rewrite it. It's just a polynomial. Just find the integral as we did it before. Okay, solution. Let's find the integral. -1 to 2, 4x cubed minus 2x plus 2dx equal to, you know that Popper rule. 4 is a number, keep it, add 1 to the power to the top, x to the 4th over 4, done. Next, minus 2, add x squared over 2, done. 2, remember the 2 is like 2x to the 0, it's going to be 2x. No constant c because of -1 to 2. Even if you write it down, it would be cancelled out. So if there is no number, you add the constant c and you're done. If there are going to be numbers, you remind yourself that I have to evaluate it. This is the notation we use. Evaluate it from -1 to 2. For the definite integral, you see, f of b minus f of a. Simplify it first, then substitute. So these two would cancel out. We get x to the 4. These two would cancel out. We get negative x squared. And this would be just a 2x. To be evaluated from -1 to 2. Carefully substitute. 2 first. 2 to the 4th minus 2 squared plus 2 times 2. That's the first part. Then for the rest, you see minus. Open up the parentheses all the time because there is a negative sign here. Now replace the x by -1. So that gives -1. Okay, -1 to 4th minus -1 squared plus 2 times -1. Carefully substitute. Any question? Do the algebra. 2 to the 4th, 16. 2 squared, 4. 2 times 2, 4. Minus inside first, simplified first. -1 to the 4th, +1. -1 squared is +1, but it's going to be -1. Okay, 2 times -1 would be -2. Equal to. So 4 and 4 cancel out, that gives us 16. Over here is going to be minus. Inside, this would cancel out, we get a -2. So it's going to be 16 plus 2, which is equal to the 18. The final answer. You see, it can be area under the curve, 18, or it may be improbability, the probability of having something. And in future, it's going to be different things. So it depends. Okay, so that gives you the final. You see, the answer must be a number. You don't have to rewrite it, but I rewrite it to explain it. So integral from -1 to 2, 4x cubed minus 2x plus 2 dx is equal to the 18. And you're done. See, it's easy procedure, of course, you know. But we gave you those examples first, okay, so that you are going to appreciate what I did over here. Any question? So make sure you know the difference. This is a definite integral, so the result must be a number. You see, it's a definite integral. The result must be a number. So you integrate it as usual. You may use different methods, even you may have to use substitution method. Then don't add the constant c. As soon as you simplify it, then you have to find it from -1 to 2 according to the fundamental theorem of calculus. We put the top numbers first. Okay, the top number first, minus. Make sure to open up the parentheses for the next group because of the negative in the formula. Then simplify it, give us the final answer. Okay, that's step 1. Any question? So everything we did before was for this one only. Okay, those partitioning one that I did just was to justify this result, okay, to get this one. So let's give another one, the type that you did before. See how about this one? Integral from 1 to 4. 1 to 4, 6 radical x. 6 radical x minus 5 over x squared plus 1 dx. You see this one? Remember, without 1 and 4, we did it before. But you got 1 to 4. So this is a definite integral again. Maybe area under the curve or maybe something else. So what do you have to do? Fundamental theorem of calculus. We forget about the numbers, we integrate it. To integrate it, we see the radical. We see the quotient. You know that. You rewrite the radical and the quotient, you move it up. All the procedure that you did before, okay? We do those first and then we evaluate it. Okay, ready? Solution? Rewrite it. So if you rewrite it, that give you 1 to 4. It's going to be 6 x to the half minus, you see, you move this one up, minus 5 x to the negative 2 plus 1 dx. That's it. Now integrate it. Equal to 6 is the number. Add x to the 1/2 plus 1, 3/2, divided by the 3/2. Done. Next, minus 5 x to the, add 1, negative 2 plus 1, negative 1, divided by negative 1. Integral of 1. Remember, 1, we want that function whose derivative is 1, is x, 1x. But it's a definite integral. So it's going to be evaluated from 1 to 4. No constancy, remember. Any question? Simplify it first, then substitute. You have the 3/2 here, you have to use the reciprocal. So it's going to be 6 times reciprocal. 3/2 would be 2/3. 2/3 x to the 3/2. Okay, that's 1. Negative, negative, positive. Positive. Okay, positive, you know that the 5 goes on the top. And you bring the x down. 5 over x. Okay, and the plus x. Plus x. Any question? But remember, it's going to be evaluated from 1 to 4. Remind yourself. So we can simplify these two. So that gives us a 2. 2 times 2 would be 4. Okay, so we end up with 4. 4x to the 3/2. Okay, everything else is going to be the same. 5x, and this is going to be x. But it got to be evaluated from 1 to 4. Substitute. X equal to 4 first, minus x equal to 1. So it's going to be equal to 4 first, 4 times 4 to the 3/2, plus 5 over x, but x is 4, plus x, x is 4, minus, open up the parentheses, repeat it for x equal to 1. X equal to 1, that gives just 4. And that gives just 5. It's going to be 5 over 1 and 1. Okay, we replace x by 4 first. Then minus, when you replace it, okay, replace x by 1. Then simplify. Start with the 4 to the 3/2. 4 to the 1/2 would be 2. 2 cubed would be 8. Okay, so this is going to be equal to 4 times 8. Okay, 4 times 8, so we just continue with the rest. It's going to be 5/4 plus 4. Now minus, work inside this parentheses. So that's it. 5 over 1 would be just 5. 4 and 5 would be 9, and 1 would be 10. So 10. Apply the negative sign. This is going to be 32. Okay, 32, that's going to be 5/4 plus 4 plus 10. Okay, plus 10. So what do we have? We have a 32 and 4, 36. 36 and 10 Okay, so that was a 32. The sign, I missed the sign here. Yes, a negative 10. Okay, so minus 10. Repeat it again. It's going to be 32 and 4 would be 36. I have 26 now. So that would be 26 plus 5/4. Okay, common denominator would be 4. So it's going to be 4 times 26. 4 times 25 would be 100. It's a 104. Okay, 104 plus 5, which is going to be 109 over 4. Final answer. Okay, again, you don't have to, but I rewrite it to show you. Integral 1 to 4, 6 radical x minus 5 over x squared plus 1 dx happen to be equal to the 109 over 4. Again, it can be area under the curve, or it can be anything else. Okay, so all sort of integral that we did have before. Now we can bring it up here into this new concept. Okay, new concept of the definite integral, or just the Riemann integral that we are going to have. Okay, any question? Now, these are the fun part, of course. Okay, but remember we did have 2 groups of integrations. One of them that ordinary function, we're just using the power rule. But the second one was what? Was the method of substitution. So you may get involved with the method. You see, you should be able to find any integral now, but it depends on the function. So if your function is going to be of a type of the chain rule type, then you should be prepared. You should be prepared to use the method of substitution. So we usually give you one problem on this one, on the next test, and on the final, it's 2 parts. The first part is one of these one that I did, but the second part is a substitution type. Okay, so you should know it yourself that you have to use the substitution type. Okay, so we are going to get the substitution type. So that's part 2. Number 3, I give you all the possibilities. And this is one of them. They usually give you a radical function, those chain rule type. And you must know it yourself that you have to use the substitution method. Okay, there you are. How about the integral from 0 to 1? Okay, integral from 0 to 1 is square root of 1 plus 8x dx. That's it. It's a definite integral because 0 to 1. So we have to use this integral. We have to find this integral first with whatever method we know. And then we come back and we substitute for the 0 and 1. To find this integral, of course, you have to rewrite it first. Okay, so the solution is going to be, you rewrite it, it's going to be 0 to 1, parentheses, 1 plus 8x. Okay, everything to the half dx. This is going to be the question. Now, as you know, this must be done by substitution method because you have a parentheses, raise it to a number. If you have this type of problem, substitution method only. In this case, you got to be careful to do your substitution. So you know that the substitution method is that you are going to check this one. You take this one to go to the u, okay? And then you must end up with, so this is going to be your target. So your u would be, okay, you take the u to be 1 plus 8x, okay? And remember the target is going to be u to the half du. This is going to be your target. So go through the procedure of the substitution method. We have to find the du. Remember the du is going to be the derivative of the function, which is going to be 8 dx. Then we have to find the dx. So you find the dx, and the dx would be du over 8. Okay, that's going to be the one. Now, you have an extra job The extra job is when you go back for your integrations. You see over here is definite integral in terms of the x. X goes from 0 to 1. But when you change it to the substitution, it's going to be u. So what are you going to do about these numbers? There are two different ways to do it. Some people ignore it, and at the end, they just get the x01. But the other method that would be more interesting, and if you want to take calculus 2, 3, in fact, today I'm going to teach this one exactly in my calculus 3 course. So the other method really is that when you want to do the substitution method, you should also substitute for this 0 and 1. So what you have to do is see, or usual, define the u, define the dx, extra job. What is the extra job? So you have to change these numbers into the u. So say, oh, x is equal to the 0, when x is equal to the 0. So what would be the u number now? You put it here. So it's going to be 1 plus 8 times 0. So that gives 1 plus 0, which is equal to 1. So when you go to the u, your integral starts from 1. Okay? Then you have x equal to 1. So when x is equal to 1, then you find your u. So it's going to be your u is going to be 1 plus 8 times 1. So we get 1 plus 8, and that would be 9. Okay, so this is the way I do it. I change the numbers. But there is, let me finish it, then I give you another, show you another method. But you better do this one really, if you want to continue taking calculus courses. So now we are ready to substitute. So when you do the substitution with the definite integral, you not only substitute for the u and the dx that you got it, but also you have to take care of your numbers. You cannot use the same numbers. So this is what we are going to be ending up. We have the 0, 1, and 1 plus 8x to the 1 half dx. So what's the conclusion? Now it's going to be integral. You cannot say 0 to 1 anymore because you change it. Now you know that 0 would change into 1. 1 would change into the 9. So integral would be 1 to 9 because you change everything into the u. Okay, now 1 plus 8x would be u to the half. And you multiply by dx. The dx is du over 8. You see? Easy integral to operate. Okay, you cannot simplify it, but there is an extra part, 1/8. Remember? You pull out the 1/8, you get your target. 1/8 integral from 1 to 9 u to the half du. Any question? So make sure that when you go to the u mode, if you like, everything must be in u mode. I mean, these numbers that you got over here. Now integrate. It's going to be 1 over 8. You know that would be u to the 3 half divided by the 3 half. But going from 1 to 9. Okay, use the reciprocal. 1/8 reciprocal of the 2/3 would be 3 half would be 2/3, and the u to the 3 half from 1 to 9. You can simplify the 2 and the 8. So you end up with what? This is going to be 1, and this is going to be 4. 1/12. 1/12 u to the 3 half from 1 to 9. You don't have to get back to the x. You just substitute the numbers that you got because you changed them. Okay, so the next step is going to be 1/12 u equal to the 9, and 9 to the 3 half minus 1/12, 1 to the 3 half. Any question? The other method that some people they do, maybe even in your book, they don't go to these red numbers here. They stay with the u. If you stay with the u, when you got over here, they change it to the x again. When they change it to the x, then they substitute 0, 1. But this method is much, much easier. because you don't have to change the u into the x because you just already changed the numbers. Okay, but anyway, if you do the other method, I know accept it too. But this is a logical, okay, method that we have. Now, continue simplify. 9 to the 1/2 would be radical 9, which is 3. 3 cubed would be 27. Okay, so this is going to be equal to the 112 times 27. Okay, and this is just a 1. It's going to be minus 112. So the top would be 2712 minus 112. So 27 minus 1, 26 over 12. And of course, you have to simplify the fraction. So that give you by 2, that give you 13, by 2, that give you 6. So integral from 0 to 1, radical 1 plus 8x dx is simply 13/6, the final answer. Okay, it's a very nice procedure, and the definite integral and the substitution methods, it's going to be hand in hand, very important problems. Most of the application types integrations are going to be involved of this method. Okay, so just take my recommendation, change the numbers as well. Okay, do your substitute, or if you don't like this one, you have to do the substitution method separately. Okay, then you come back and substitute. We don't mind. Both of them would be fine. Okay, any question? I need to give you one more of this substitution method, and this is where you get that trigonometric function that we talk about it. And this is very popular. And then we're done. You know that these are part of the 4.5 as well. So what else do we need to know is there are some properties of this definite integral that would be useful. And so we talk about those properties tomorrow. And then we are done with chapter 5. So we give you the test. And after your test, we just taking chapter, this is chapter 4. Then we take the chapter 5. It's just a special functions, exponential function, log function, and inverse trigonometric function. And then we are done. Okay, so the crunch is going to be this chapter 4 to take care of it. The rest are going to be a special function. Okay, now this integral is also very famous. It's this type, 0 to radical pi, that's it, x sine of x squared dx. It can come with a sine, cosine, tangent, secant. You will see one of them in your next test and on the final. Okay, these are going to be almost the same, x squared, x cubed, x to the 5th, etc. We cannot make it complicated because of the nature of this course, but you will see them in calculus too. Okay, now, why we like it? Because we like it to use the substitution method for this. Remember, we talk about it. If it's going to be anything other than the x, you take this one to be u, and then you operate it. So this is it. Solution. A solution is going to be, we have to do a substitution method. You take this one to be u equal to the x squared. Okay. So your target is to change this one into the sine u du. That's the target. Okay, so you have to find the du. Du is 2x dx. And we have to find the dx. So the dx would be du over 2x. Go back, substitute. But since you get the 0 and radical pi, you have to switch the numbers too. Okay, this is the place that you may make a mistake. Say, oh, are you ready to do the substitution? No, I'm not ready because I have to take care of these numbers. X equal to the 0, change it to the u. Plug in, would be 0 squared, which is 0. So this stays 0. But x equal to the radical pi, I find the u, which is the x squared, is the radical pi squared, which is equal to the pi. Okay, so integral from 0 to radical pi would be changed into the integral from 0 to pi. Make sure to change this one too. Okay, any question? Go back, substitute for everything. So this is the original one, 0 to radical pi, x sine of x squared dx. 0 is 0. Radical pi would be changed to the pi. We don't have anything for the x, nothing to worry about. Sine of u, but multiplied by dx. And what is the dx? Dx is the du over 2x. Simplify. Left over a half. So it's going to be 1/2 integral from 0 to pi sine u du as you targeted. Okay. So integral of a sine, you know, there is a negative cosine. So it's going to be negative 1/2 cosine of u, but it's going to be evaluated from 0 to pi. Again, you don't have to go back, change it to the x because you already changed the numbers. So simply substitute, it's going to be negative 1/2 cosine of the pi minus negative 1/2 cosine of the 0. Cosine of the pi is a negative 1. Cosine of the 0 is 1. So negative positive, that give you 1/2. Negative positive, that give you 1/2. 1/2 and 1/2 would be equal to 1. So that integral, okay, integral 0 to radical pi, okay, x sine of the x squared dx is equal to 1. And then you're done. Okay, so this is the way we are going to use that fundamental theorem of calculus. For this, there are a couple of shortcuts. I talk about it later for the application, but these are very standard and you should know them, how to operate. Okay, so the conclusion from the argument today is you are going to have 2 problems or 3 problems really. And so far, one of them is those partitioning one. You see, I didn't use partition for each, but one of them would be given to you. You see, that's the one that we did. We give you something easy. We're just going with the x squared because, you know, we don't want to make it complicated, but we want to know this. So see, this is use a definition. If you say use it the definition, this is the only one. If you use this method, you get no point for it. Okay, but for the usual evaluation of the definite integral, of course, we are using the theorem that we talk about it. So one question, but we are going to check it on on Thursday. We check that that review that I posted for you, test 3, is a part of your final review as well. Okay, and so there are a couple of more properties. We talk about it tomorrow, and we finish this chapter 5 on time. And on Thursday, we go over the solution of that practice test number 3 that I already posted for you. Of course, your lowest test score and lowest quiz scores would be dropped. But even if you already got the 2 nice points on test 1 and test 2, my recommendation is just keep up and prepare the test 3 for yourself, because you can drop your lowest, you know, I will drop your lowest exam, even if it's going to be 100. But that test 3 would be fully come back on the final. So don't slow it down, really. Just keep up and just be prepared, because, you know, 2 weeks time, so we get the final. Okay, so we continue tomorrow and we finish this chapter. There is just a couple of things, more thing to talk about it, but otherwise we are going to start reviewing. Okay, that's it. Any question? So I've already posted all the results of the test 2. So if you have any question on those, just let me know. Okay, have a good one. Take care and see you tomorrow. Bye-bye.